in current, electricity, internal resistance and electromotive force of the cell, terminal potential difference of a cell, expression for internal resistance, cells in series and cells in parallel. Today I am going to discuss all the topics step by step. First one, internal resistance of a cell. The resistance offered by the electrolyte of the cell when the electric currents flow through electrolyte is called internal resistance and represented by a small r. Electromotive force, the potential difference between the two poles of the cells in open circuit when no current drawn from the cell is called electromotive force, that is EMF of the cell. It is represented by E. E equal to dW by dq. Hence, work done per unit charge is also said to be electromotive force and its unit is joule per coulomb. This is the watt volt. Terminal potential. Next topic, terminal potential difference of a cell. The potential difference between the two poles of a closed circuit when current is drawn from the cell is called terminal potential difference of the cell and represented by V. Here figure, cell connected with what? Key and external resistance R, voltmeter connected parallel with the cell. So when current flows through the circuit, then there is fall of potential across the internal resistance of the cell. The potential difference between two poles of the cell is less than the EMF of the cell. Now, expression for internal resistance. Here, again we draw the diagrams here that cell connected with the key and external resistance R, voltmeter connected parallel with the cell. Okay, to consider a cell of EMF E and internal resistance R connected with external resistance R in circuit, voltmeter connected in between two terminal of the cell. When current is open, then no current drawn from the cell. Okay, when circuit is open, then no current drawn from the cell, then V equal to E. When circuit is closed, then current draw from the cell and I equal to E by R plus R. The terminal potential difference V is smaller than EMF, electromotive force, by an amount equal to the potential drop across the internal resistance of the cell. So that's why V equal to E minus IR. When no current drawn, then V equal to E. So also terminal potential difference is equal to the potential difference across the external resistance R. Okay, so V equal to IR and V equal to E by R plus R into R, or R plus R equal to E by V into R. So R equal to E by V, R minus R, take the R common, then its value equal to R common, then E by V minus 1. So a small r equal to E minus V by V into R. Now next, cells in series. Cells in series. Here n number of cells connected in series with external resistance R. So n number of cells connected in series with external resistance R shown in the figure. The negative terminal of the first cell is connected to the positive terminal of the second. Negative connect with positive terminal of the second, and the negative terminal of the second cell is cell to the positive terminals and so on. So total EMF of the cell, here n number of cells and each cells have EMF E. So total EMF of the cell equal to NE. And each cell internal resistance is R. So total internal resistance equal to R plus n times dot n times, so its value equal to NR. So total resistance of the circuit equal to NR plus R. If I ampere current flow across the circuit, then I equal to total EMF by total resistance. So I equal to NE by R plus NR. When R is smaller than NR, in such a case, R plus NR equal to NR. So I equal to NE by NR equal to E by R, and this is the what? Current due to single cells. But when R is greater than NR, in such a case, R plus NR equal to capital R. So I equal to NE by capital R. This is the what? This is the what? N times the current due to single cell. In order to have maximum current, the cells should be connected in series when the total internal resistance of the cell negligible as compared to the external resistance of the circuit. Now, cells in parallel. Consider here n number of cells, each of EMF E and internal resistance R connected parallel and in parallel combination, connected in series with external resistance R. In parallel, positive terminal of all the cells connected at one end and negative terminal of all the cells are connected to other ends. The parallel combination, total EMF of parallel combination remains equal to the EMF of single cells. So total EMF equal to E. So total internal resistance represented by R dash. So 1 by R dash equal to 1 by R plus dot M times, and its value equal to what? M by R. Okay, so R dash equal to R by M. So total resistance in the circuit equal to R plus R dash equal to R plus R by M. So current across the circuit I equal to E by R plus Rm. Now, in a special case, if R is greater than R by M, then R plus R by M equal to R. So I equal to E by R, and this is what? Current due to single cell. But when R is smaller than R by M, then R plus R by M equal to R by M. So I equal to E divided by R by M equal to M E by R. So its value equal to M times the current due to single cell. In order to have maximum current, the cells should be connected in parallel when the external resistance in the circuit is negligible as compared to the total internal resistance of the cell. Thank you. Have a nice day.